let's explore inflation. This is a very fun time to talk about the theory of inflation, because just 2 days ago, inflation was awarded the Kavli Prize right here at the World Science Festival. And this is a very happy day, not only for Alan Guth and Andrei Linde and Alexei Starobinsky, who won the Kavli Prizes, but also for the many other people who contributed in various ways to formulating and developing this fascinating theory of inflation. So what is inflation then? It's the most popular theory right now for what actually happened early on, for what created our Big Bang. And what is it that the theory says? Well, it has only one single assumption that you need to make. You need to assume that there is a tiny speck of matter, vastly smaller than a proton is plenty enough, that has a strange property that it's very hard to dilute. So that if you expand it into a larger volume, its density stays almost the same. That's very different from everyday stuff like air, where if you put it in a larger volume, the density drops because the total mass is the same. If you have this kind of inflation substance, you have 1 kilogram of it, you put it in twice the volume, well, now you've got 2 kilograms. If you are willing to assume that such a substance exists, then you can prove by just plugging it into the theory of general relativity that it will create a Big Bang for you. Specifically, what comes out of the equations very beautifully and caused Alan Guth to write on his notes spectacular realization when he figured this out, is that it will just keep doubling and doubling and doubling itself at regular intervals. In the simplest models, it doubles every hundredth of a trillionth of a trillionth of a trillionth of a second. Okay? So you have one little speck of the stuff, then you have twice as much, twice as much, twice as much, twice as much. And you all know that repeated doubling rapidly creates an enormous amount of things. And it's not just the amount of stuff that goes up vastly, the number of kilograms, but also the speeds involved keep doubling, as you can see from the doubling of the length of these arrows, right? So even if the motions are very slow and insignificant, pretty quickly you have enormously high speeds. If you plot here how big this clump is as a function of time, you realize actually that our universe's birth, according to inflation, was very similar to our own. Because we started out being 1 cell, then we were 2 cells, and 4 cells, and 8 cells, 16, 32, 64, and so on. Fortunately for our mommies, we didn't keep doubling for 9 months, because then the delivery would have been a little bit painful. We would have had more mass than the mass of our universe. Instead, what happened is that when we were about this big, this doubling stopped and gave rise to more leisurely growth, which is why we were about this size at 9 months. And interestingly, our universe did exactly the same. Through some strange coincidence, it's the same y-axis on both of these plots. When our universe was about this big, it stopped inflating. The horizontal axis, on the other hand, is very different. We humans, we doubled about once per day. Our baby universe in the simplest model doubled every hundredth of a trillionth of a trillionth of a trillionth of a second. Then did so maybe 80 times, perhaps a lot more. Okay? You only need one assumption to get this, but you get a lot of predictions out. This is a theory that gives much more out than you put into it. What does it predict? Well, first of all, it predicts that there will be a Big Bang. We just saw how this repeated doubling actually causes a Big Bang. Okay? So it solves the bang problem in the sense that in traditional cosmology, if you're asking, well, what caused the Big Bang, you're like, awkward silence, because there is no explanation. The equations simply assume that it happened. It's very unsatisfactory that you have to start out with an infinite space, which somehow, for some weird reason, all started expanding exactly uniformly, all at the same time, all with the same temperature, all with the same density. Basically, you need to start with some sort of miracle. Inflation, on the other hand, says, no, there's no miracle at all. You just need this puny speck, less mass than that of an apple, much smaller than a proton, and then it predicts our Big Bang, making everything we see here in our cosmos. It also predicts something else. It predicts that what we see should look almost exactly the same in all the different directions. So you, the keeper of our universe, if you look closely at the universe there, you'll see the temperature is varying by 1,000th of a percent from place to place, but that's not much, right? Why is it not 50 times hotter on one side than the other? You might think, well, when you pour cold milk into warm coffee and wait a while, it also all acquires the same lukewarm temperature. So maybe that's the explanation for why our universe kind of has the same temperature everywhere. Except in traditional cosmology, that's an epic fail. It doesn't work at all, because the light from the region A has only now just barely reached us here at the halfway point, at the same time as the light from the other side has just barely reached us. So there's been no time at all for any communication between these two parts, let alone more time for energy to flow back and forth and equilibrate the temperatures to all be the same. Right? This is what Alan Guth called the horizon problem. How did these parts know to have the same temperature? Well, inflation solves that and predicts that everything should have the same temperature, because it says that early on there was this tiny speck. It could have been hanging around doing whatever it did for a long time, reaching a kind of uniform temperature, and then we're all inflated at a vast speed, and those temperatures were the same because the conditions had already been set up to be kind of the same throughout that tiny little speck. Inflation also predicts that the space we observe in our universe should be almost exactly flat, that the angles of a large triangle in space should add up to 180 degrees. Why does it predict that? Well, if you take something like a curved space here that the ant is on, right, and you inflate it up to an enormous size very quickly, light doesn't have time to go very long distances in that short time. So what the ant is going to call its universe, the part that light has reached it from, is just a tiny fraction of the whole sphere, which was going to look very flat to the ant. Just like if you're out in the middle of the ocean is going to look pretty flat to you because you're seeing just a small, small part of Earth. So inflation predicts that space should be very flat, which also solved the so-called flatness problem, because it was well known that if you just tweak the density of the universe a billionth of a second old by just changing the last decimal place here a little bit, the whole thing would have collapsed together in a black hole long ago, or totally diluted itself away long ago. Yet somehow it had exactly the magic density, exactly the magic flatness to last this long. Well, inflation explains that. Inflation predicts still more stuff. It also predicts that our universe was not completely uniform early on, but had these tiny little fluctuations, which we previously just had to assume were there, right? If our universe had started completely uniform, we wouldn't be having this conversation today, because then it would have to stay completely uniform. And we would never have formed this large-scale structure, the galaxies, the stars, the planets, or the World Science Festival. What was it that created those seed fluctuations? What was it that created effectively the cosmic DNA? These early 10 to the minus 5 level fluctuations, these patterns that indicated like a blueprint where the galaxies were going to form and where we would instead form giant voids. Where did that come from? Well, inflation predicts that they were there. And the prediction it gives is actually, in my opinion, one of the most beautiful ideas in all of science. By connecting two things which seem completely unrelated. Inflation says that they come from quantum mechanics, from the Heisenberg uncertainty principle, which says that you cannot have anything completely uniform. The Heisenberg uncertainty principle says that if you have something completely uniform, you're not actually allowed to know exactly then the velocities of your particles, and pretty quickly they're going to start moving and become non-uniform. But how could possibly these quantum fluctuations, which we know to be important today only on tiny scales, have anything to do with the scales of galaxies? Well, because inflation stretches space by this stupendous factor. Right, so these tiny quantum fluctuations get stretched out to scales of galaxies and beyond, and predict that actually the ultimate origin of the largest structures we see in our universe, like superclusters, comes from quantum fluctuations in the subatomic realm. And this isn't just a bunch of nice-sounding blah, blah, blah. We can turn this into equations and make very rigorous predictions for exactly how clumpy our universe should be on different scales. And this is something I've spent many years of my own career doing precision measurements of with my colleagues, and it agrees beautifully, beautifully with the predictions from inflation. Not only for the galaxy clustering, but also if you look in detail at these hot and cold spots in the cosmic microwave background, these baby pictures of our 400,000-year-old universe. If you want to know, if you make a histogram and you want to know how many spots are there of different sizes, it agrees beautifully with the prediction of inflation. Finally, the most audacious prediction of all from inflation is that there should be gravitational waves in the simplest inflation models, ripples in the very fabric of space itself that are huge, of order billions of light years in size. And this had for many years been considered sort of the holy grail to look for this. And something that would be viewed as a smoking gun of inflation if it were found. And then just this spring, it was announced by the BICEP team that they had found it. And there were a lot of smiles all around, including at MIT here by Alan Guth and Andre Linde, who happened to be visiting. The little dark cloud over their heads here is a dust cloud, because there's an interesting discussion going on right now about whether this is really what the signal is that they've seen, or whether contamination by radio noise from dust in our galaxy might play an important role. We're going to have to wait until the end of this year with a lot more data coming in to know for sure. But this is another example of a spectacular prediction. It's a very audacious one, too. It's the most audacious extrapolation ever of known physics to 100 billion times higher energy than we've tested in the Large Hadron Collider, and 38 orders of magnitude earlier in time. And so if this holds up, it'll be just absolutely spectacular. Now, that's the good news about inflation. For as long as I've been in cosmology, I've also heard a lot of my colleagues criticize inflation, and you'll also hear an interesting balanced assessment of this from the next speaker, Paul Steinhardt, here today. Some of the most common complaints about inflation are, first of all, this assumption, the one assumption that there could be a substance that isn't diluted by expansion. That sounds kind of nutty. How could you possibly have that? Except that now we know there is such a thing, dark energy, which was discovered and got the Nobel Prize. It's precisely that kind of thing. So that argument is kind of moot now. Inflation is simply dark energy, but much higher density, so things double much faster. Then people have made the objection that, well, okay, the most popular physical model for what such a substance could be is called a scalar field. It's like a cousin of the magnetic field, which instead of having a strength and a direction at every point in space, like the magnetic field does, has only a strength. It's like a number everywhere in space. And people will say, well, this is kind of speculative because we haven't found any scalar fields in nature. Except that now we have, as of last year. The Higgs boson, the Higgs field is exactly a scalar field. Finally, people have said that, well, inflation doesn't really make testable predictions. But actually, specific models of inflation certainly make testable predictions. In fact, the simplest model of all, where the thing that specifies a so-called potential energy function is simply a parabola, look at all the predictions it makes. Loads of things. The business about space being flat is parameterized by a number called omega. Inflation predicts it should be 1. I and many of my colleagues have been involved in measuring it. It's 1.001 plus minus 0.007, so it agrees with the prediction to 1% accuracy. That's pretty awesome. 2 smiley faces for that. And a lot of other predictions that are in very good agreement, and other predictions where we don't really have the measurements yet, but people are working on making the measurements better. So this is science at its best. Inflation sticks its neck out, makes a lot of predictions, and we're working on testing them. So I think we should do we know that inflation happened? No, we don't. Is it a scientific theory? Absolutely. Should we take it seriously? Yes, absolutely. And if we do, then we also have to take seriously what it predicts. Not just for these numbers, but also conceptually. One of the things we have to take seriously is that we need to change the way we talk about our Big Bang. For example, I cracked up when I read this article in the New York Times here where it says that actually inflation caused this rapid expansion in the instant after the Big Bang. No. Inflation didn't happen after the Big Bang. It makes no sense at all to say that the beginning or the early stages of inflation were a hot Big Bang, or after the hot Big Bang, because at that time it was neither particularly hot or particularly big or particularly bangy. right? It got much, much hotter, hundreds of thousands of times. It got 1,000 times hotter once inflation stopped. In the beginning of inflation, it was not that big. It was less massive than an apple, right? Less than a billionth the size of a proton. And it was really not much of a bang, because the expansion speeds back then were a trillion times smaller than after it ended. Okay? Instead, a much better way of saying it is that the early stages of inflation was a cold little swoosh. And then eventually it picked up steam, and this cold little swoosh caused our hot Big Bang.